All right, we're going to talk about enthalpy today. And what I'm going to do is read along with this. For those of you watching the video, you can skip through this if you don't want to hear the reading, but I will also pause and explain some things. So we're going to start with enthalpy. Enthalpy, almost all chemical and physical reactions involve energy, usually in the form of heat, being released or added. An exothermic change is a reaction that releases energy. An endothermic change is one in which the energy must be added for the reaction to occur. For exothermic reactions, energy can be thought of as a product in the reaction. For endothermic changes, energy can be thought of as a reactant in the reaction. So what I'm going to do here is highlight some things. I'm going to say exothermic reaction, energy, product. And then I'm going to highlight endothermic, energy, reactant. Whenever we set these equations up, that's where you will see energy within the equation. Exothermic is going to have it as a product. Endothermic will have it as a reactant. Enthalpy, abbreviated capital H, is the energy or heat content of a system at constant pressure. You cannot measure the actual energy or enthalpy of a substance, but you can measure the change in enthalpy for a reaction. This change is symbolized by delta H of reaction. The way we get that is we take the H of the products and subtract it from the H of the reactants, the enthalpy of each one. Exothermic versus endothermic. For exothermic reactions, enthalpy values are always negative. That is, the energy of the product is lower than that of the reactant. So what I'm going to do here is highlight exothermic reactions. Enthalpy values are negative. Exothermic has a negative delta H. So the energy of the products is lower than that of the reactants. Remember, heat is given off in that in an exothermic reaction. So that's what's happening. The energy is going to be lower in the product because heat has been released. This is because energy is released as new bonds are formed in the products, and this amount of energy is greater than the energy required to break old bonds in the reactants. For example, we got an equation here. 4 moles of iron reacts with 3 moles of oxygen to produce 2 moles of iron oxide. And then our delta H for this reaction is negative 1625 kilojoules. So that means we have a negative heat, or the heat is being released. And then you can see that here, where instead of having delta H written, they've actually incorporated that heat into the equation. Remember up here we said exothermic reactions are in the product. Energy is going to be as a product, and that's where we have energy is on the product side. This means that when Fe2O3 is formed, the reaction will release 1625 joules of energy. The reactants have more energy than the products, and that energy was released. For endothermic reactions, enthalpy values are always positive. So endothermic reactions, enthalpy values are always positive. That is, the energy of that product is greater than that of the reactants or reactions. This is because the energy released as new bonds are formed in a product is less than the energy required to break the bonds in the reactants. This energy must be supplied in order for the reaction to occur. The added energy does not disappear, of course, due to the law of conservation of energy. Instead, it becomes stored in the chemical bonds of the products. So looking at this example, we've got carbon plus H2O yields CO plus H2. And then what we got here, the delta H is positive. So you can see the big difference. In this equation, heat is added into the reactants. It's on the left side. So anytime you have heat on the product side, that's an exothermic reaction. That's heat being released. And then if you have heat on the reactant side, on the left side, that's heat being put into the system. So that is an endothermic reaction. This means that when CO and H2 is formed, the reaction will absorb 113 joules of energy or heat. And the products have more energy than the reactants, so that energy must have been absorbed. Energy diagrams. The energy diagrams to the right show an example of both an endothermic and exothermic reaction. For the endothermic graph, notice how the products are at a higher energy than the reactants were, so delta H is positive. For the exothermic graphs, notice how the products are at a lower energy. So what I want y'all to see real quick on here, if this is measuring energy on potential energy here, this is heat. We started low, and then you can see here this curve. This is the energy to get the reaction going. It's called activation energy. Once we get that reaction going, we eventually finish and the reaction stops when it flattens out right here. But if you notice, the products is a higher amount of energy. We put energy into the system. So this is an endothermic reaction. Heat entered the system. We started with a low amount. We finished with a higher one. So delta H here is positive. Now on the right side, this one's an exothermic reaction. We said that exothermic means exit. You can see on the graph that we started with a high amount and we finished with a lower amount. So delta H is negative. The change in heat is positive, the graph will finish higher. If the change in heat is negative, the graph will finish lower. That's how you can just look at a graph and determine whether we're absorbing or releasing energy, just based on that alone. Stoichiometry, that's what we had in our warm-up today. Chemistry problems involving enthalpy changes are similar to stoichiometry problems that we learned how to do previously. The amount of energy that is absorbed or released in a reaction depends on the number of moles of reactants involved. Think about this in terms of dynamite. If one stick of dynamite causes a small explosion, you would expect 10 sticks of dynamite to cause an explosion 10 times the size. For example, according to the following equation, 113 kilojoules of heat is absorbed when 1 mole of carbon reacts with 1 mole of water. How much heat will be absorbed if 2 moles of carbon combine with 2 moles of water? If you said 226 kilojoules of heat are absorbed, twice the amount absorbed by 1 mole of each of the reactants, you are correct. The enthalpy change for a reaction is proportionately smaller or larger depending on the amounts of the reactants and products involved. So what that's saying here is if 113 kilojoules is how much heat is required to absorb for 1 mole of each of these reactants, if you double the moles, double the reactant, you're doubling the amount of heat needed. The same thing with recipes we talked about, stoichiometry, those rules apply. An example problem here, how much heat will be released if 1 gram of hydrogen peroxide, H2O2, decomposes? You can see the equation here, 2 moles of hydrogen peroxide yields 2 moles of water plus 1 mole of oxygen. We've got a delta H as negative, so that implies that we're releasing heat in this equation. Whenever we set up our train tracks, we're starting with 1 gram of H2O2. We convert this back to moles using our molar mass from the periodic table. And then this 2 moles comes from the equation up here. So 2 moles is going to go right here. And then that negative 190 comes from our delta H, how much heat is released. So what we're doing here is we're multiplying the top, dividing by the bottom, and then we get our answer. We are going to work through a couple of those in the following example. So what we're going to do now is I want y'all to go to the next part of this, and we're going to fill this part out together. So I want y'all to help me real quick. When a reaction is exothermic, what type of delta H does it have, positive or negative? What do we say from the notes? If it's exothermic, heat is being released, that's a negative delta H. If heat is being absorbed, if we're adding heat to it, what's the sign for that one? Positive. That's an endothermic reaction there. So which has more energies, reactants or products? In an exothermic one, our products are going to have more energy. In endothermic, our reactants are going to. Because in this one, we're adding heat into those. That's what we got for that. Number 2, does the energy go from the surrounding to the chemicals or from the chemicals to the surroundings in an exothermic reaction? Where's the heat coming from here? In this one here, heat is coming from the chemicals, and that heat is being released to the surroundings. Think of an exothermic reaction as giving off heat. That's what's happening here. So it's going from the chemicals to the surroundings. Classify each of the following as exothermic or endothermic processes. So what we have to do is think about, are we adding heat or are we releasing? So in this example here, to melt an ice cube, do you have to add heat or take heat away to melt an ice cube? To go from a solid to a liquid, do you add heat or take heat away? You add heat. So what type of reaction adds heat? Endothermic. This one's endo. Burning a candle. Does a candle give off heat or absorb heat? A candle gives off heat. If you've ever seen a candle before with the fire burning, that's an exothermic reaction. Evaporation of water. To go from a liquid to a gas, do you have to add heat or take heat away? You have to add heat. So that is an endothermic reaction. You're absorbing heat. To bake bread, do you have to add heat or take heat away? You add heat. You put it in the oven. So this one's an endothermic reaction. It absorbs that heat. To split a gas molecule apart. What do y'all think here? To break that bond. If you want to break a stick, you have to put energy into that. Same thing for a molecule. This one's going to be an endothermic reaction. How about formation of snow in the clouds? You have to add heat or take heat away. All right, for snow in the clouds, we're going from gas to liquid to solid to form that. So now, my question here is to go from gas to liquid to solid. Are you adding heat or taking heat away? For things to condense. And then for things to freeze. You got to take that heat away. So this one's going to be an exothermic reaction. Next part we're going to do here is sketch the graphs. We've got A, B, C, and D. We're going to go and work A real quick. First thing we got to figure out is this an endothermic or exothermic reaction? Where is heat at in this equation here? Is it on the reactant side or the product? It's on the reactant side. So we're putting heat into this system. So we're going to start low, and we're going to have our curve that shows the reaction, and we're going to finish high. It doesn't really matter where you put it on here, but we're starting low, and we're finishing high. We're absorbing that in. And then delta H is this gap from here all the way to this part right here. So delta H, is it going to be positive or negative here? Did we gain heat or did we lose heat? We gained heat. In fact, we gained 20.3 kilojoules. That's how we write that one. So we started low, we finished high. On letter B, where is heat in this equation? Is it in the reactants or the products? This time it's in the product, so we're going to start high, and we're going to finish low. We're giving off that heat. That heat is being released. So same thing here. Delta H is this gap in between where we started and where we finished. And this one here, delta H is equal to positive or negative 127 kilojoules if it's giving off heat. Negative. This one's negative since we decreased in value. For letter C, notice now delta H is given to you. It's not a part of the equation, but it tells you here this is solid going to aqueous. So we're losing heat on here since it's a negative value. We're going to start high and finish low. And then our delta H here is equal to negative 82.8 kilojoules. And then the final thing here, it's positive, so that means we're absorbing that heat. We're starting low, finishing high at 49. Our delta H is equal to 49.0 kilojoules. Just like that. That's how we do those. So you have to determine if it's endo or exothermic, and that will determine the shape of your graph. Endothermics absorb, they get bigger. Exothermics release, they get smaller. They start high, finish low. Next thing we're going to do is we're going to work these examples down here. For number 5, what we're going to do is look at this problem. How much heat is released when 9.22 grams of glucose in your body reacts with according to the following equation? So our goal is to figure out how much heat is released for 9.22 grams. The equation tells me how much heat is released for 1 mole of glucose. We want to know how much heat is going to release for this many grams of glucose. First thing we're going to do is set up our train track. 9.22 grams of C6H12O6. We're going to draw our train track. We're going to take grams of C6H12O6, and we're always going to go back to moles whenever we're at grams. And that's because the equation that they're giving to you here is set up for moles. We know the amount of heat for 1 mole. So here we can use our conversion provided. 1 mole is 180 grams. This is exactly what you did in the warm-up. Grams cancels out. I'm left with moles, but we're looking for heat. So we're going to continue this down. We're going to bring mole of C6H12O6. And this time we're going to go up to kilojoules, which is our unit for heat. And they provide this to you in the equation. They show you that 1 mole of kilojoule, 1 mole of glucose is going to produce negative 2,803 kilojoules. We do want that negative value since we're releasing heat, because that's going to show us how much we're changing. So last thing we have to do now that this is set up, we're going to multiply across the top and divide by the bottom. So now that I have my calculator here, we're going to do 9.22 times 1 times negative 2,803. And then I'm going to divide that by 180. And then I have my answer here. And we can go and round that to negative 144 kilojoules. And then now we have our answer. So we notice that it's a lot less than this value here, but that's because this value is for 1 mole, which was 180 grams. We've only got 9.22 grams, so it should be way less than the other value. That's all there is to that. Not super difficult. Number 6, how much heat is absorbed during photosynthesis when 9.22 grams of glucose is produced? So this time, the only difference here is we're absorbing. We've flipped our equation. We've reversed that. So we're going to start with the same thing, 9.22 grams of glucose. We're going to draw our train track. And we're going to take grams of C6H12O6, and we're going to go back to moles, just like we did a second ago. That's because our equation is set up for the number of moles for heat. 1 mole is 180. That comes from adding all these up. They went ahead and provided that to you in the problem. Grams is going to cancel out. We're left with moles, but we need to get to heat. So we're going to take moles of C6H12O6. 1 mole of this is equal to, it tells you here, positive 2,803 kilojoules. And then whenever I do the math, it's going to come out to the same answer. The only difference is, what do we notice about the difference in these answers? One is negative, one is positive. The way you figure that out is if you're releasing heat, it's a negative. If you're absorbing heat, it's positive. Let's go and look at number 7 next. How much heat is released when 147 grams of NO2 is dissolved in water? We're going to start with 147 grams of NO2. Going to draw my train track. We're going to bring grams of NO2 to the bottom, just like we did before. We're going to go back to moles of NO2. 1 mole of NO2 is equal to 46 grams according to the problem. That's also from the periodic table. That's 14 plus 16 plus 16 for N and O's mass. Grams cancels out. I'm left with moles, but we're looking for heat. So we're going to continue this one step further. We're going to bring moles of NO2 up to kilojoules. Now this one we got to look. We got to make sure we check this. It was 1 mole in the last problem because it was only 1 mole of glucose in these questions. But the difference now, when we look at NO2, how many moles of NO2 are in this equation? There are 3. So this number down here is going to be 3 moles of NO2 and it will still be negative 138 kilojoules right here. But that 3 is because of there's 3 moles of NO2. So for 3 moles of NO2 in the rest of the equation, you're going to release negative 138 kilojoules. So now what we can do is multiply the top, divide by the bottom. We can figure out our answer here. 147 times 1 times negative 138 divided by 46 divided by 3. And then we get our answer here. Negative 147 kilojoules. That's negative because we're releasing heat. Last thing on here, calculate the heat released when 74.6 grams of SO2 reacts with the following equation. So for this one here, we've got 74.6 grams of SO2. Do the same thing we've been doing. Bring down grams of SO2. We're going to go back to moles of SO2. It's always 1 mole whenever we're doing grams. This time they didn't provide it to us, so we're going to have to go find it. If we look at the periodic table, S is about 32. So if I have SO2 and I need the mass, S is about 32, and I've got 1 of them. And then O is 16, but there are 2 of them. So that's 16 times 2. That's 32. If I add those together, I get to 64. And that is our mass for that. Grams cancels out. I'm left with moles. But we've got to get to heat. We're going to bring moles of SO2 to the bottom. We're going to go to kilojoules up top. We have to go look at our equation. How many moles of SO2 are in this equation? It's 2. Pull that number from the front. 2 moles of SO2 will release negative 99.1 kilojoules. Just like that. We multiply the top. 74.6 times 1 times negative 99.1 divided by 64 divided by 2, and we get negative 57.75. We can go ahead and round that to negative 57.8. Negative 57.8 kilojoules. Once again, it's negative because we're releasing heat. We are going to look at one final thing on here. We're going to go ahead and run down this list, and then that will finish out our lesson on this part. Answer the following questions about the reaction shown below. C2H5OH plus 3 moles of O2 yields 2 moles of CO2 plus 3 moles of water, and delta H for this is negative 1,360 kilojoules. Letter A says, is this reaction endothermic or exothermic? Are we absorbing heat or releasing heat? What do we think here? Releasing heat. How do we know? It's negative. Delta H is negative. The change in heat is negative. We're getting rid of heat. This answer here is exothermic. We are decreasing the amount of heat that we have. Rewrite the equation on the line below, but we're going to include the energy term in the reaction. That means we're going to take delta H and actually put it a part of the equation. We're going to set up the same thing here, C2H5OH plus 3 moles of O2 yields 2 moles of CO2 plus 3 moles of H2O. And now we need to decide, where does our 1,360 kilojoules go? Does it go on the product side or does it go on the reactant side? The left or the right? We have to know about where that heat value is. So if this is an exothermic reaction, where is heat at? Are we putting it into it in the reactants, or are we releasing it with the products? We're releasing it. So our final thing on here, we're going to write plus 1,360 kilojoules, just like that. So I know we said it's negative, but when we're writing it as the equation here, it's still a part of the system, we write plus that heat value. But that is releasing that much heat. That's what it's saying there. Letter C says, what is the change in enthalpy, the delta H for products versus reactants, if 3 moles of ethanol react with excess oxygen? What we have been doing was going grams. We're just going to make it easy. We're only going to have to do moles. So this time we're going to set up 3 moles of C2H5OH. Now we're going to set up our train track here. We're going to go moles of ethanol, which is C2H5OH. We're going to go up to kilojoules. Looking at our reaction here, we can see in this equation that we set up here, 1 mole of ethanol is going to release negative 1,360 kilojoules. We'll multiply that top, divide by the bottom, so it's 3 times 1,360 kilojoules, but it is negative. Our final answer on that one would be negative 4,080 kilojoules. Just like that. Letter D says, if 4 moles of carbon dioxide are produced by the above reaction, how many kilojoules are released? We're going to do the same thing, start with our given. This time we're doing CO2, so 4 moles of CO2. We'll bring mole of CO2 to the bottom. We're going to go to kilojoules on top. And then what we have to do there is set up our numbers based on the equation. For CO2, it's 2 moles. That's what we had in this question up here, or in the equation provided. So that's 2 moles of CO2 will release negative 1,360 kilojoules. I'll write my number 2 here, and then negative 1,360. Moles of CO2 gets canceled out. I'm left with kilojoules. The last thing we need to do is multiply the top, divide by the bottom. We take 4.00 times negative 1,360 kilojoules divided by 2. And then my final answer on this one's negative 2,720 kilojoules, just like that. Last question, what is the change in enthalpy, or delta H, for the products versus reactants for the burning of 1 gram of ethanol? So this last thing we're going to do on here for that letter is we're going to convert 1 gram of ethanol, which it did tell us up there at the top that ethanol was the C2H5OH. And then we're going to take the molar mass of that and go from grams to mole. We'll go grams of C2H5OH to mole of C2H5OH. And you've got 2 ways you can do this. At this point in the year, you can calculate it yourself, or you can look it up online. If we look it up online, it comes out to 46 grams per 1 mole. Grams cancels out. I'm left with mole, but we're looking for the heat since we're looking for delta H. And then we're going to bring mole of ethanol, which was C2H5OH, up to kilojoules. And we need to go back to our parent equation to figure out our mole for ethanol. If we go back and look, ethanol was 1 mole. Will release negative 1,360. 1 mole will release negative 1,360 kilojoules. And the last thing I need to do is multiply the top and divide by the bottom. So that's 1 times negative 1,360 divided by 46 divided by 1. And then we get an answer of negative 29.6 once we round that. Negative 29.6 kilojoules. Letter F says, draw a sketch of the energy diagram for the reaction. Which has the higher enthalpy in this reaction, the reactants or the products? Explain. When we start our graph, are we going to start low and finish high, or start high and finish low, since this one's exothermic? We're going to start high, and then we're going to finish low. So we're going to have our curve. We're going to finish low like that. And then this one here, we can see that the delta H on this one is, if it's for 1 gram, we could put that on here. But since we don't know which amount we're doing, what we'll just say is delta H equals negative value. But we do know the value. We know that it's negative 1,360 kilojoules, since it tells us that. So up here, it does say that. So we can write that number. And then for this one here, we know that it's an exothermic reaction. That means that heat is released. And therefore, it's a lower enthalpy for the products, since that one's going to have a lower amount on an exothermic. I know that was a long video, but if you need to go back at any point, you can watch any of those examples again.